Right, so before moving forward, let's quickly recap what we covered in last session, and then in this session my target is to discuss different problem types and their solution techniques in this rectilinear motion part of this course. So let's have a quick recap. The first thing we discussed in last session was that that velocity is ds by dt, right? S is the position coordinate, v is the velocity. We can also write it as ds is equal to v dt, right? We can take its integration on both sides. We can write it as ds starting from some initial value of s, let's say s naught, up to a certain value, let's say s, will be equal to v dt, and the limits of t will be from t equal to 0 to a particular time t, right? We also saw the geometric interpretation of this equation, and that geometric interpretation was that the area enclosed by v versus t relationship, right, between any two time instants t1 and t2 is equal to the net displacement, right, net displacement between t1 and t2. So you can evaluate this integral analytically also, but also graphically, right? The second concept we discussed was acceleration is equal to dv by dt, and that is actually dv is equal to a times dt, and again we can write it in integral form, and that was dv from v naught to some value of v is equal to a dt integral, where limits will be from t equal to 0 to some value of t, right? Again we have a graphical interpretation of it, and that is the area enclosed by the acceleration versus time relationship between any two time instants t1 and t2, that is equal to net velocity between the same time t1 and t2. So these are the two graphical interpretations of these relationships, and we also saw a third relationship which was actually relating all three quantities, and that was v dv is equal to a ds, right? So we call them equation 1, 2 and 3 respectively, and we saw their both analytical formulation and the graphical formulation. This third equation is actually relating all three quantities: the position coordinate, displacement, the acceleration and velocity, right? So now let's see that in how many ways we can use these three relationships to solve all problems in the rectilinear motion part. So we may be having different problem types. For example, some problem type may give you the displacement versus time relationship and ask you to determine velocity versus time. Some may say that acceleration is available to you, but calculate velocity and displacement respectively, right? So there can be several problem types, and each will require a different solution technique. So I will be actually using analytical integration. So we may be solving those problems not graphically but analytically. So we will be actually solving the integral equations or differential equations. So the first concept is that if S is known for all values of time t, if the value of S is available to you for all time instants, we can do successive mathematical or graphical differentiation with respect to time to determine velocity and acceleration. So it's simply application of the equation 1 and equation 2, right? So if S is available to you as a function of time, for example, if I give you S is equal to 2t square plus 5, right? So now it is a quadratic equation in t which is relating the displacement with time, right? You can plot that equation for different values of time, and then you can again imagine how that motion would look like, right? So this is an example of when S was given to you for all time instants in the form of a function. In this particular case, it was a second degree polynomial or quadratic function, but S can also be given as any other function type also, like trigonometric function or logarithmic function. S can be given as a exponential function of time, right? So any function is available. You can, if the function is available, then you can differentiate it with respect to time to get velocity. You can differentiate it one more time with respect to time again, and to get acceleration, right? So that is actually the first problem type which you will be facing in this topic, rectilinear motion. By problem type I mean what is given to you and what you are required to determine, right? Let's see one example of this problem type, and I think instead of directly solving that problem, I will first clearly state that what problem type it is to make the solution approach more clear. So for example, the position coordinate of a particle which is confined to move along a straight line is given by this equation, right? So in most cases when there is a confined motion, the particle is required to move in a particular path, you will always be having the displacement coordinate described as a function of time, because that particle mostly is designed to follow a particular path in a given time. So you can describe its path by a continuous function of time. For example, here you are given a cubic polynomial S is equal to 2t cube minus 24t plus 6, right? So it's a cubic equation in t which is relating time and position coordinate, right? And S is in meters and t is in seconds, so it's a system international problem. So you are required to determine three things. A is the time required for the particle to reach a velocity of 72 meter per second. So you are given with a velocity and you are asked to determine at what time the particle will have that velocity. So particle is moving in a straight line, rectilinear motion, and that motion is described by this equation. But you are required to determine that at what time the particle will have a velocity of 72 meter per second from its initial condition at t equal to 0. Similarly, the second part is that you are required to determine the acceleration of particle when velocity was 30 meter per second. So now again a given velocity is there, but you are now required to determine the acceleration when the velocity was 30 meter per second. And lastly, you are required to determine the net displacement of a particle between given time intervals, two different time intervals, t equal to 1 up to t equal to 4 seconds, right? So instead of directly starting the solution, let me clearly state what type of problem it is, and then you can apply the same idea or same solution approach to not only this one but all the category which is having the same problem type, right? So let me call this thing as problem type 1. Problem type 1, right, in rectilinear motion. So clearly state, let's see what is given. So for given, we are actually having S is given as a function of time, right? So actually S versus T relationship is given analytically, not graphically, but the equation is available, which means it is analytically available, right? So S is as a function of time, S versus T relationship is available. So it is an analytical relationship which is actually a third degree polynomial, right, in time. Let's see what you are required to determine. So to determine in this particular problem, if you look at the A, B and C here, you will see that in first case you are required to determine a time corresponding to a particular velocity, which will actually require you to have a velocity time relationship so that you can put a particular velocity in it and get the corresponding time, right? So in order to solve A, you need to get velocity versus time relationship, or you need to convert S versus T to V versus T, right? So the first thing to determine actually is V versus T, velocity expressed as a function of time, and then the same thing, for example, you need to determine T for a given value of V, right? So you can do that from exactly V versus T relationship. So I can just combine them as one unknown thing. First you will determine V versus T and then put a particular value of V to determine the value of T, right? The second thing was the value of acceleration is to be determined for a given value of velocity, right? So the second step actually will require you to determine a relationship between acceleration versus time first, right? And then you will see that from first relationship you will determine at what value of t your v is 30, and then from the acceleration versus time relationship you will calculate what acceleration it is at that particular time, right? So for example, if it is asking me to determine acceleration when v was 30, I will still use velocity versus time relationship, put 30 in it to determine at what time velocity was 30. And then from the acceleration versus time relationship, I will put that time in that to calculate the acceleration, right? And third part is the net displacement of particle during the interval from 1 to 2. So let me just write it as C, which is net displacement. So let's call it delta S, right? Which will simply be the value of S at a particular time minus the value of S at some other time. So let me just call it as ST2 minus ST1, right? So if it is saying what is the net displacement between 1 second and 4 second, so it is simply asking me to determine the value of S at 1 second and then at 4 second, and then subtract them, actually S4 minus S1, right? Net displacement. This is if we decide to solve this problem analytically. We also know that we can graphically determine the area enclosed by V versus T relationship to calculate any net displacement between any two time instants, but that will be applied if we decide to solve this problem graphically, right, not analytically. So that C will actually doesn't require anything, it will simply require the same given relationship. So in the same relationship you will just put t equal to 4 second, get the value of displacement, t equal to 1 second, get the value of displacement, right? And then you can subtract them to get the net displacement or delta S, right? So the solution approach for this should be, if for example we require velocity versus time with a given S versus time, the solution approach should be to differentiate that with respect to time. So let me just continue here with solution approach, right? So in order to calculate, if you go back, see the first thing you need is the velocity versus time relationship, right? And that can be determined by differentiating S versus time. So for A, you can say that my solution approach is to differentiate S versus T relationship with respect to T, right, to actually get the V versus T relationship, right? So the whole equation which was available, I should differentiate with respect to T. It was already a function of T, I differentiate it to get velocity, right? So S versus T, which was given, differentiate it and get V versus T. Similarly, for second part where you were requiring acceleration versus time relationship, you need to repeat that one more time. So differentiate V versus T, which you just determined in part A, with respect to time again, to get A versus T, right? A versus T. So you will be actually getting both V versus T and A versus T. Once you have these two relationships from the given S versus T relationship, now you can answer all those questions like what was the time when velocity is this much, what was the acceleration when time was this much, right? Or what was the acceleration when velocity was that much. All those questions can be answered once you have these two, A and B. So for any other thing to be determined, actually you will be using both A and B again and again. So A and B will be again and again used to answer any other questions about velocity and acceleration, because once you have their relationships with respect to time, you can always answer questions like what will be the time corresponding to a particular value of velocity, right? So I repeat again this whole idea that I defined a problem type 1 and I will be actually defining some other types also, like 3, 4 or 5 types of problems. But this particular problem, it has a S versus T relationship given, and you are required to determine velocity and acceleration, right? And the solution technique, if I summarize it in one line, it would be differentiate the S versus T relationship in successive times, 2 times actually, one time to get velocity versus time and second time to get acceleration versus time, right? So I found it very useful to classify problems into different categories based on what is given to you and what needs to be determined. And then whenever you see a new problem, just try to find which category it is, what is given, what is required to be determined. Once you do that, you should be quickly able to come up with a solution approach or technique applied to approach that solution, right? So first type, displacement given as a function of time, velocity and acceleration is to be determined. So now this problem, let's come back to the same problem that S was given 2t cube minus 24t plus 6, and you are required to determine a particular time corresponding to when velocity was 72. Actually V versus T relationship need to be determined first, and then we put V equal to 72 to get the value of time. So if I start the part A first, so let me just separate that part out, and I am now starting the solution of this problem. For part A, I am given with S is equal to 2t cube minus 24t plus 6, right? 24t plus 6. So and I want to determine the time corresponding to velocity was 72 meter per second, right? This is to be determined. So the relationship between V and T need to be determined. The solution approach which should automatically come in your mind is to differentiate this equation with respect to time, right? So let's do that. V will be equal to ds over dt, or we also can say using equation 1. So actually it is equation 1 in what we discussed previously. So that will be d by dt of 2t cube minus 24t plus 6, right? This should give you actually equation for V, and that is actually 6t square minus 24, right? This is the first derivative of S with respect to time, and that is velocity. So now this is a 2-degree polynomial, a quadratic equation in T, which is relating velocity for any time t. Once we already have the V versus T relationship, now in order to solve for the first case A, all we need to do is to put V equal to 72 here to get a particular time to answer the part A, right? So what I am simply doing here in this part, that I am putting V equal to 72, is equal to 6t square minus 24, and when you work that out it should come out to be t equal to 4 seconds. It will be plus minus 4, but you shouldn't consider the minus 4 as the right root, because t in minus would actually mean that the motion haven't yet started. Motion started from t equal to 0, that was given in the problem, right? So therefore we should discard the second root, which is minus. So at 4 second actually the velocity of that particle will be 72, right? If you plot that equation which I encircle, you will also be seeing it graphically that at t equal to 4 second, the value of velocity on y-axis will be 72, right? So let's move to the second part, and for that we need to differentiate velocity versus time relationship to get acceleration, because second part is about acceleration. It is saying the acceleration of a particle when velocity was having a certain value, right? So in order to proceed for part B, let's start with the velocity equation which we just determined. It was 6t square minus 24. Let's differentiate it one more time. So A will be dv by dt. Actually what I am doing is I am applying equation 2 here. So that will be actually d by dt of 6t square minus 24, which will give me A is equal to 12t, right? So I get a linear relationship between time and acceleration. It's a function between time and acceleration, and it is a linear relationship, right? So now the question says that what was the value of acceleration when v was equal to some value. V was equal to 30 meter per second here. So let me just go back there. When v is 30 meter per second, so what should we do? We need to first determine that time at which velocity was 30, and then put that time in this equation to get what acceleration would be at that time, right? So in order to get the time corresponding to v equal to 30, let's use that top equation again, maybe here. So I am putting v equal to 30 is equal to 6t square minus 24. That should actually give me t equal to 30 plus 24 divided by 6. So you can work that out. I think it will be 3 seconds. This time I will write correctly. And again I would ignore the negative root for that equation. It actually should be t square here, right? So now we know that velocity is having a value of 30 meter per second when time was 3 seconds. So let's now put that into our acceleration equation. So acceleration when v was 30 should be equal to 12 times 3, and that should be 36 meter per second square, right? So B was done also, and the main idea was to calculate acceleration as a function of time by differentiating the velocity time relationship. And once you have that equation, then you can answer all those questions like what was the value of acceleration at a given time, or you can also find questions asking if the acceleration is equal to this much meter per second square, what will be the corresponding time, right? So that can also be asked. Now finally the third part, which is simply asking you to determine net displacement, and that doesn't require you to apply equation 1 or equation 2. That simply will be actually using the given relationship. So net displacement of that particle during the interval from t equal to 1 to 4 seconds, right? So we should first put t equal to 1 second, then we should again put t equal to 4 second, and their difference should be the net displacement, right? So C part is the simplest one actually. So C will be simply S is equal to 2t cube minus 24t plus 6. So let's first calculate S of 1 second. That will be some number. Then you can calculate S at 4 second, right? So by putting, for example, 2 times 4 cube minus 24 into 4 plus 6, right? So you will be getting the displacement at 4 second. And then in order to calculate the net displacement, that should be s at 4 second minus s at 1 second, right? So it's just a way to write the value of displacement at a particular time, right? So please don't confuse with this notation. Sometimes the textbooks use, for example, S4 minus S1, right? So they can mention time step in the subscript also. It doesn't matter, but the value of S4 minus S1 or 4 time instant minus first second, you can get that difference and that will be your final answer, right? So now let's finally try to imagine that equation, like how physically that motion would look like. Let's quickly plot it for, let's say, first 4 seconds, right? So let me just quickly say that t was, let's say, 0, 1, 2, 3 and 4 second. So it is t in seconds. And let's calculate s from the same equation. So let's try to plot it and visualize it. For t equal to 0, it will be plus 6. That will be 0. Second term will also be 0. For t equal to 1, it will be 2 minus 24 plus 6. It will be what? Minus 16, right? For t equal to 2 seconds, it will be 2 times 2 cube minus 24 into 2 plus 6, right? It will be what? 16 minus 48 plus 6. It will be what? Minus 26. Similarly, we can also put t equal to 3 and get the corresponding number, and then t equal to 4, you can also repeat that, 2 times 4 cube minus 24 into 4 plus 6. You should get, from this you should get plus 38, right? So if I plot that s versus t, it is looking something like this, like at t equal to 0, the value was plus 6. At t equal to 2, the value goes to minus 26. So let's say 0, 1, 2, 3 and 4. So at t equal to 1, it's minus 16. So something like this, minus 16. Then at t equal to 2 second, it goes to minus 26, something like this, minus 26. And then you will be having some value at 3 and 4, it again goes to plus 38. So it's something like going to plus 38 at t equal to 4. So it's plus 38. So now let's try to make a picture in our mind. So it's started, if I am standing at origin, the particle started its motion at 6 meters from me towards my right, and then it started coming towards me, past me at this particular time, and goes to my left as much as a distance of 26 meters. Then it changed its direction and again start coming towards me, pass me again at this particular time instant, and then goes again to my right to as much as 38 meters at the end of 4th second, right? So you can imagine how that motion would look like, right? So please always try to confirm your analytical solution with your graphical interpretation. For example, at 26 seconds, you came to know that the value of s was maximum. Before 2 seconds, the value was less than maximum. After 2 seconds, the value is less than maximum in a particular direction. So which means that the slope of s versus t at this point is 0, which means you should have velocity equal to 0 at time t equal to 2 seconds, right? So you can quickly confirm that from the second part by putting t equal to 2 seconds. So 6 into 2 square minus 24, that is equal to 0, right? So you can always confirm your graphical interpretation with your analytical solution. Let's finally, in the same problem, let's plot all 3 equations, s versus t, which was given, which is this one, velocity versus t, which we calculated after differentiating it first time, and acceleration versus t, which we differentiated one time more to get that. So let's call that given equation as equation 1, right? Similarly, the velocity versus time equation 2 and acceleration versus time equation 3. If you plot all three equations, you will find something like this, that we already have determined. When you plot the second equation, that was actually 6t square minus 24, v is equal to 6t square minus 24, and that linear line is actually a is equal to 12t, right? So when I am asking in part C, for example, that calculate the delta S between t is equal to 4 second and t equal to 1 second, I am graphically asking you to determine this shaded area, right? Shaded area in the v versus t relationship between the same two time instants, t equal to 1 second to 4 second. So this shaded area is actually graphically equal to the part C, the number which you will be calculating. It will be actually 54 meters, right? S4 minus S1, right? S4 minus S1. So in this particular case, since these are cubic or polynomial equations, so you might not easily determine graphically the areas. But what if I give you a, for example, second degree polynomial for S versus t, you differentiate to get a linear equation as v versus t, just like here, right? So if you plot a linear equation, you should be graphically be able to determine the area enclosed by that curve, right? So please think of all possible types of problems which you can put in the same category, right? So your goal shouldn't be just only those problems given to you as a tutorial set, but they are actually representative problems of another category of problems which may have many variations in them, right? Similarly, you can be given, for example, S versus T relationship in the form of some other like weird looking polynomial, or it can be even a trigonometric function also, but it will always be relating time with distance, right? So you should be able to get its first derivative, second derivative easily by applying your basic calculus methods, right?